Okay, so this is the wildcard detector complex consisting of these 4 parts. Our first part is the roller coaster spiral particle accelerator. As you can see, it is in the shape of a roller coaster, and that's the important innovation that we use because the shape of the roller coaster decreases the digging cost because instead of spreading it out with smaller sequential in 2D like kind of plane, we have the smaller piece starting at the very bottom, 200 meters deep, and then it gets larger to the main accelerator. So the particles we used were a proton and a positron. These two are positive and they would yield good results, but other than that, we really don't have any special reason for using these 2 particles. So we use the proton in the spiral accelerator, and we use the positron in the linear accelerator because the positron would suffer from synchrotron radiation if it were in a spiral. So we decided to keep it in the linear accelerator just to increase the energy. So the proton is in 10 different layers here in our spiral accelerator. So each one is double the radius of the previous. So you can't really tell in this illustration here, but it is exactly double each of the radius of the previous circle.
Okay, so good afternoon. So as my partner just stated, our accelerator is a linear, multi-circular hybrid design. The reason why we did this way is because like she said, it was efficient because of economic and logistics. So first what happens is that 200 meters below the ground, a proton starts in its proton source, and it goes through a small linear accelerator until it reaches our first and smallest circle, which is also 200 meters below the ground. The circular accelerator, it will then accelerate the proton to enough energy to go to the next level, which is 10 meters, to spiral up to the next level, which is 10 meters above the small one, and it's also double the radius, and it produces double the energy. And then it repeats that 8 times until it gets to the top, which is 100 meters below ground level, where it meets the linear accelerator, a longer linear accelerator with, on the other end, a positron source. The positron source sends positrons, of course, to the linear accelerator, and they collide in the largest circular accelerator, which is 125 kilometers in radius. Giving a center mass energy of about 374 tele-electron volts.
Okay, this is the luminosity of our accelerator. So I want to note that that the luminosity is on the order closer to 10 to the 37th, which you may want to compare it to some of the other groups. It was calculated using this equation here. We have the frequency, the frequency, and then n1, n sub 1, n sub 2, which are the particles of each bunch that are collided, and that's over sigma x and sigma y, which are the widths of the beams that are being collided. The collision frequency was about 750 million hertz, and in order to calculate that, we used the distance between each of the bunches that were coming out of the source to be collided. And then for both the amount in the bunches, it was like we have a 10 to 12 particles in each one, and then the beam widths 2 times 10 to the negative 5th meters in the x direction, and in the y direction 0.4 meters, which is the distance between each bunch.
So I have a lot of trouble understanding that. You have 10 circular accelerators?
Yes, we are using 10 Tesla magnets, that's what I forgot to point out, and also the scale of size shown in the pictures.
Ginormous is the word you're looking for.
Yes, ginormous. IMSA is right along there, and we have a, that will be where the linear accelerator order to be up.
So you have 10 circular accelerators.
Yes.
Does the positron ever go in a circle, or is it only in a linear accelerator?
No,
It's only-
it's just linear. Straight in the
What made you want to go 200 meters underground? Why don't you just have a circle with a smaller circle with a smaller circle? I mean, I'm just thinking about mining costs, digging that. Why don't you just, rather than spiral downwards, why not just have a circle with a smaller circle with a smaller, you know?
So what do you mean?
But why not just, that and then that, all on one level? Like 10 meters underground rather than digging 200 meters underground. Why the cone thing? You get this thing, right? You get the tornado.
Yeah.
Why the tornado? Why not just push them all up under one layer? What was the reason for going underground?
I don't think the materials on the outside of our beam pipe and our other materials would let us smush them in that way.
I think it's a magnet issue because we're using magnets. I think that's the reason why we did that.
I believe Mike has an answer. He's also part of our group.
The reason they did it is the original design, they wanted to create a amusement park within.
It was also, we were also hoping for an innovation in the way. We were hoping for something new and maybe this would create those results.
But if you cost it out, I think it's killing you. Okay.
We are still under budget. That's the important part of $40 million.
We finished the music part.
Yeah.
Yeah, with our leftover money, we plan to create a music park on it.
Wait, fundraiser. Now we're going to take a look at the detector complex to begin with the small tracker within. Our tracker is very, very small. At 70, it is a series of concentric spheres. At its largest point is 70 centimeters, so about this big. It is quite dense, however. It contains 23 layers of silicon pixels, with the 10 innermost layers containing a maximum channel density of 10 to the 8th, and and at the other layers, all containing a maximum sensitivity of a still respectable 10 to the 7th.
Okay, so the way we do the energy analysis is, if you visualize it, you'll have the inner sphere of the tracking detector, the outer sphere, and then some sphere in between, and a deflection of 1 pixel in either direction on the middle sphere allows you to geometrically calculate the radius of the particle that, or the circular path that the particle will take inside our solenoid's magnetic field, and that also allows you to calculate using P equals BRQ, that allows you to calculate the maximum potential momentum that we can measure with the detector, which is 125 TeV, which is about 1/3 of the maximum energy of accelerator.
So our overall building and excavation cost is about $510 million, and our readout cost for channels and whatnot is $940 million about. So our total is a little less than $1.5 billion, and the rest of it, which is a little over $1.5 billion, went to the muon detector because they went over budget because they didn't know the cool stuff. So that's tracking the detector phase. Disappointed that we're all wishing to sit with me.
You didn't say anything about your magnet. Tell me about your magnet.
It's a 13 Tesla solar.
So,
We didn't talk about it because it also includes the calendar.
Yeah.
Something that's not.
so you have a spherical tracker with a cylindrical magnet. Just like okay.
No. All right.
The solenoid is a cylinder, and your detector is spherical.
Any other questions?
No, I'm good. Running out of time, I can only do so many. We're gonna spend about an hour each next time.
You got a little extra time now. Because they
Alright.
rearrange things.
So our calorimeter is a Star Trek.
Wow.
Anyway, it's the Death Star Super Calorimeter Boy. Anyway.
Trademark.
So we have two parts. We have the, we acronize everything here. So ECal and the HCal for the electron calorimeter part and the hadronic calorimeter part. The electron calorimeter consists of 39 spherical layers. And this spherical design we use to increase accuracy because it allows the same material for each of the particles to pass through. Whereas if you're using a cylinder's design, you have to compensate with discs and there's patches that you have to fill in. In addition, it decreased the material that we had to use because there's a lot of excess space when you're using a cylinder, whereas a sphere, it kind of condenses everything down. And those 39 spherical layers consisted of lead tungsten. This was chosen because it has a relatively small radiation length in comparison to the other materials we were offered. In addition, it has dual properties of being able to absorb and detect the energy because of its crystallized structure. So, and this also reduced space. And that helped on cost, kind of. I mean, this material itself was expensive, so it was give and take. And connected to the lead tungstate was the avalanche photonides, which were compatible with our solenoid since the calorimeter is inside the solenoid because the magnetic field has a tendency to affect the different detectors, and the avalanche photonides it does not. So that is our main reason for using that. In addition, our solenoid, I know you had questions with this with previous groups, it's composed of several different cylindrical layers. So it would look very similar to a sphere, but it wouldn't be a perfect sphere design. Instead, it would be several cylindrical layers. So it would be like, think of a donut sitting on top of a larger donut.
I understand the geometry.
Yeah.
Right. So then after the ECal comes the HCal. So the HCal consists of 53 spherical layers for the same reason that we made the ECal spherical. We wanted to cover more angles of potential particles flying out of our collisions. So we made the shape spherical so that we could cover all the angles. After filling the ECal with a bunch of lead tungsten, we realized that we were running a bit less on money than we thought we might have. So we cut down on cost of it. We used cheap options like iron absorbers and plastic simulators, which worked just as well as other options we had. In fact, we originally were toying with the idea of using liquid argon scintillators, but we found that plastic scintillators were actually better for what we were looking for in that particular regard. So we used plastic scintillators and iron absorbers in our HCal. We again used avalanche photodiodes, utilizing avalanche effect, and allow for higher energy resolutions.
Okay, so for our energy analysis, we use that equation up there, where Fx is a fraction of original energy deposited by particle per x radiation length slash radiation length. And then A is this equation where E is the original energy, which for this case is 1/3 of a center of mass energy, so 125 TeV. And then EC is the critical energy of lead tungstate for the ECal, and then iron for the HCal. And so with this equation, we can calculate the percentage of energy deposited, which is the sum of Fx times x for each layer of the calorimeter. And then we can calculate the percentage of energy collected, which is the sum of Fx times x for each layer of scintillator of the calorimeter. And so for the energy deposited, it was 99.18% for a proton and 99.71% for an electron. And then the energy collected would be 17.43% for a proton, and then the 99.7% for an electron.
Is that all calorimeter? All right, so I have a big question. Your ecal, you have 20 whatever layers of
39.
39. Okay. So am I understanding this right? That there's like a sort of a thin layer of this tungstate, and then a gap, and then another thin, just.
They're pretty much right on top of each other. So.
Okay. Why do you have 39 layers? I mean, why do you have any layers? What's the rationale for layers?
The layers are in part so that you can detect how much energy is being absorbed per layer. So, as a particle,
That I understand. What information does that give you?
it gives me. So if, say, we don't detect all the energy, it gives me sort of the decrease it does. So we'll be able to plot that out on a graph sort of thing. So if it decreases this, we'll be able to find the kind of 100% of the energy that it originally had with it.
But it was 99.2% or something like that, right?
Yeah, it was not. You're right. It's fairly accurate. So it's basically so that we can have a better graph plotted.
Well, because the graph is actually like, since the thing we're taking is like the area under the curve, and if we just had one layer, like one solid block, then it would give us a really inaccurate calculation, because then the area under the graph wouldn't work, versus if we do our calculations using a lot of layers, it'll distribute that throughout the graph more evenly and we'll get a better, more accurate answer.
You sure about that?
Not anymore.
Case in point, CMS has one layer.
Yeah.
Yeah. Like 39 just allowed us to calculate it easier. Like
integrating it over the whole thing and having one interval is the easiest. I was just curious, sort of just quickie. How thick were you thinking the lead tungstates be?
The lead tungstates are going to be 0.0068 centimeters.
Wait, 0.0068 meters, you mean, right?
Meters, sorry. It's in meters.
So it's half a centimeter?
6.8 millimeters.
Yeah, 7 millimeters.
Okay. That's what I was curious.
Alright, now let's talk about the muon detector. A large, integrated, collision keeper muonic experiment.
Yeah.
Okay, so for the geometry, we decided to go with a spherical design. We have a yoke, and we're using resistive plate chambers, and we have multiple toric magnets. For the yoke, it's 12.511 meter for the radius, which is, we took the radius of the calorimeter and added 1.3 meters to it. And we also have 3 separate clusters that surround the yoke, each with 4 spherical layers of the resistive plate chambers, and they're spaced 4 meters apart. And we have 85 toric magnets with an inner circumference of 79.24 meters and an outer circumference of 129.88 meters.
Oh, circumference.
Continuing with the common trend of spherical designs, the advantage of a spherical design is the fact that now you can get the muons detected from all different angles, and the angles are relatively the same because it's a sphere, so if it's coming from this direction, the path is about the same as if it's coming from this other direction. So therefore, we can detect more muons because of the sphere, and then from detecting more muons, we can determine we can have more likelihood that we're detecting actual muons and not non-muonic particles.
I have to ask, you have lack of pseudo-rapidity. How do you lose pseudo-rapidity?
But you don't lose it.
That's what
I said we don't have to account for pseudo-rapidity as much because the angle is about the same. Well, if you...
the sphere, it's going to intersect everything perpendicular.
Yeah.
We have broken some relativity. I didn't know what it was.
Okay, so there's so material analysis. Just like the last group, the energy was about like the calculations about the same using the f of x equation that was on the slide earlier. It only changed it by a little bit. So the energy absorbed by the calorimeter was like 99.18. Now it's 99.8. So 100 minus that is like 0.7% of non-muonic. So those are the big muons. And then the interaction and radiation lengths were calculated just for the yoke. You also have to account for the solenoid because that's outside of it. Yeah.
Yeah, so the resolution analysis, we sort of did the same thing as the last group where we used our energy to calculate the radius that the highest momentum particles would be traveling. So the momentum of 1 TeV that's up there is not correct. It's actually like 20.8. We were able to do some last minute modifications to increase that momentum. But the radius is roughly 4,600 meters. And that radius gave us the spacing of 4 meters between the 3 clusters of our detectors.
Questions, comments, concerns?
Mostly concerns.
No, we're out of time. I think we get past.
Okay, so Dr. Lincoln is the one to ask. So, Dr. Lincoln, any final thoughts, and then also your decision?
Well, it's a tough one. They all have a lot of fun. So I could coin, but I don't have 3 seconds.
No, we can't hear you in the back.
Oh. So, there's a lot of effort been into all of them, so I don't, it's very difficult to make a decision. The acronyms here were very clever. However, you name something after Star Wars, and everybody knows that Star Trek is way the hell up with Star Wars.
Why would you say it's Star Trek?
I don't know, man. That's like a death knell. I don't know. Can we get 3 little gizmos and give one to each group?
Oh yeah, that's a great idea.
Yeah, I could ask the docents if they have any more. I actually got it from the actually. No.
I'll get the points.
I don't think that makes sense. But is there a real one?
That's crazy.
Don't pick
You give us all extra credit.
If you want to, the decision doesn't need to leave this room until we're off.
Right. So I don't want to be torn apart here, man.
We can be sad if you want.
Very difficult.
Yeah, right. Did you need to see any of this slightly?
No.
Yeah, it's true. Yeah.
He has his decision. Look, it's there.
Yeah, he gets like wants to keep it waiting.
If you want to make it easier for you, we can make the decision for you.
We have the best names.
You do have the best names, but you got that whole Star Wars thing.
Yeah, he's right.
Death knell. I don't know, man. I can't get past that.
It's been a lot worse.
Yeah, let's try.
I think, and this is a small point, but the only detector for which it makes any sense to be spherical is the muon detector. It makes no sense to be spherical for any of the other detectors, and I can tell you why. And it's a very small point on which to pick them, but I think that's why I picked that.
The muon, so that's number 2, right?
But you guys all did a good
I
job.
don't know this one. Why specifically for muons?
All right, think about this. So you have a muon detector, right? Like this. These are point-like particles, right? So what happens? In this case, guaranteed sum of momentum equals 0, correct? But if you have a proton, even though the momentum of the protons are exactly equal, this guy could have very different momentum. And so in every single detector, and you did CDF, right? So in every single possible collision, there is a off balance of the momenta. And so consequently, even though we can get to the center of mass frame with the two partons, in the net thing, you're still going to have a net momentum because of this off balance, right? And because of that, you have to make all of your measurements that are independent to the boosts along this direction. They have to be Lorentz invariant due to boosts. The only one for which a spherical detector can actually matter is one where the sum of the momenta equals to 0.
Does anyone have to use pseudo-rapidity?
You don't use pseudo-rapidity. Pseudo-rapidity makes no sense in a spherical detector. And it makes no sense here. Now for here, you have to use pseudo-rapidity because the delta eta is independent of the Lorentz boost. And so that's why. And so, you know, you only can use a spherical detector now, like crystal ball and jade and all those E+ E- machines back, you know, when I didn't have any gray hair when I was your age. Actually, I was your age a long time ago. We did spherical detectors because it was E+ E-, and you had the sum momentum equal 0. So all of the detectors, both, I mean, even for the, when you have one electron and one proton, you still have the issue where you've got one where you have all the sum momentum in one case, but you have variability. So
you have to do something that's not invariant.
Yeah, it has to be Lorentz invariant against boost, and that's why we do transverse momentum. In the old detectors, they never used transverse momentum, right? They just did energy because it was completely surrounded, and you had rotational invariance, everything's there. The only thing breaking, now this is not to you guys, but to you, the only thing that breaks the Lorentz invariance of something like this is the spin states.
Oh, okay.
Right? Because, well, I mean, no, they don't have to be polarized, but the point is that they are longitudinally. So,
Okay.
so on average, it won't matter, but you could make it so you break it. Otherwise, you know, these things come in, and they come out with that, or this. This whole system is rotationally invariant, whereas this has to be boost invariant. So that's the rationale.
I see. That makes sense. I think that.
So, yeah, I mean, you know, you guys did a great job. I mean, it's absolutely incredibly difficult. We could have spent a lot of time. It would have been fun talking about all of the pieces and stuff. So it's tricky, but because of the fact that that's the only one for which a spherical detector is prayer. So.
We still all give a little like. We'll have to ask Doc Sue what she thinks. But she's provided it. Dr. Lincoln thought everyone did a good job, and he's like, "We have 3 little gizmos we can give to them." And so
I only had that one. Sorry.
All right. Well, we'll give it to the group that earned it. Although it'd be better if it were a sphere, huh?
Yes.
What do you have, Alex?
Are there any other differences between any other parts of the accelerator?
You have to speak up. I heard there are any different parts, and then you dropped off.
Are there any other differences between any other parts of the different groups, or is that just the one point?
You know, you guys all. I mean, realistically, there were lots of issues with all of them, and we have to take that into account. There are things like you were all calculating the bending curvature of outrageously highly energetic particles. There were issues like the multiple layers of the electromagnetic calorimeter in the last one. I mean, CMS has one. You don't need so many of them. And I realized why you did that. You were looking for the shape, and that's great. But if you just integrate the whole thing and you know that it's deep enough, the trick is just make it deep enough. And I also, another thing I liked, it was, you know, I mean, there was so much randomness in this. Like the answer of why they had the, you know, they handled the answer of why there were multiple layers of the hadron calorimeter well. You know, I mean, it's not that anybody else did a bad job, but it was like an answer that, without hesitation, it just, you know, so it meant that they thought of that little question through.
Wait, what if the last one was in space?
With or without warp drive?
With intergalactic capabilities.
Ah, that would definitely.
Yes!
They actually, each small group had come up with a design for each of them, and they voted on their favorite ones. And one of the designs involved a space elevator and an accelerator in outer space. That's so
Expensive.
That's what they discovered.
You got it to work.
Yeah, they got to work, but the center mass energy was like 1 TeV.
And you know, just so you guys know, he was giving you like crazy amounts of money. A real detector is about $500 million. And that's a reasonable. CMS and Atlas are both $500 million each. So that's the reasonable cost. And the reasonable cost for an accelerator is of order $10 billion. So you guys had tons of money. Tons of money. If you had that kind of money, we could go and do some real damage. And you know, for $40 billion, you should have, you know, if you wanted to win, you should have had like an incredibly good coffee shop up on the top of the, you know, that kind of money.
There was a proposal that their leftover money was used to buy ice cream machines. All of it.
But they didn't say it.
That's true.
If they said it,
We had a roller coaster.
That was your guys, right?
Roller coasters normally.
Yeah, roller coasters are okay. I want good coffee.
No, you're right. Good coffee on the road. What about good coffee?
That's horrible.
I was going to mess up the phone.
Yeah,
It's going to be a really good phone.
What if the roller coaster doesn't like melt?
I have a question. What if our particle accelerator could be used for alchemy and then create gold particles out of lead that we put inside?
It's been done.
I know that,
a
but
long time ago. But not great, not huge amounts.
Not very costly.
Yeah, not very costly. It's easier to dig them out of the ground.
Well, let's thank Dr. Lakin one more time.
I was wondering about the accelerators, like what did you think about those for the different groups?
They're all
Well, I wasn't so happy with the tornado, because that was pretty expensive. The muon one had, I mean, the problem is the muon accelerator was not described as well as I would like it to, because it's actually exceedingly difficult. Protons, electrons, and the positrons, by the way, nobody mentioned exactly how you make the positrons and collect them, so I had some issues with that as well. But with muons, you have to make the detector, or make the muons. They live 2.2 microseconds, but you have Lorentz time dilation, which you guys are learning about, which helps you. But there was not enough discussion about the capture of the muons. And so I would have to say of the three, the first one had more of the pieces that were needed, but it helped because it was an easier machine. The lead, nobody's talked about, I'm not lead, the gold, but exactly how the gold, how you'd ionize the gold. I mean, that was another question. How do you pull 72 electrons off an ion? I mean, what, tweezers or what the hell do you do? That's hard. So each one of them had issues. I liked the muon one, except for this huge gaping thing of how the hell do you get muons?
For the record, guys, I did tell you how sources work. Just saying.
And then,
but we didn't go into cool.
Yeah. Well, no, you go with it. But just some step about that transition would have been good. And some statement about how you got positrons, and the last one would be good. And how you would ionize the gold in the first one would be good. But probably the first one was sort of the most. It had things that were closer to being right, but because it was easier. Right? It was easier. I mean, muons is hard. Positrons is hard. And then the other thing is nobody mentioned the fact that, I mean, when I was beating people up on the first one because we had more time for them, these magnets have to change they have to put current. You have to go from a low magnetic field to a high magnetic field. So everybody had fixed magnets.
For the record, I talked about that too.
Yeah, I was just confused because that was like a month and a half ago.
Yeah. And then the first one, the cylindrical detector for that was for the first detector is the most appropriate for this reason, although they had the spherical hadron calorimeter. Should have just stayed spherical. So, I mean, all of them were tough. You know, I mean, you guys all thought a lot and did good stuff. And, you know, if you'd had, you know, a little more time, a little bit more focus. I mean, the class is mostly on modern physics.
Yeah, I mean, mostly the learning relativity.
Right, exactly. So, I mean, but you could go through this, and it wouldn't take long. You guys would learn a bunch of this stuff. I mean, there's a whole ton of cool things you could do. And, you know, some of one of the things, there was infrequently things that, I mean, if you think about these solenoids versus, I mean, even the statement about how you had solenoids that were like so, lost it now. I mean, this is, you know, as good an answer as you can get once you say that. But remember, the magnetic field of a solenoid is along the axis, right? Mm-hmm. And so now you've got things coming out, and from the center, you were doing your V cross B business, yeah. But it's not V, I mean, you didn't have a B like that, you know, there were some issues with that. And the same thing we're talking about the correlates. Yeah, so it's really hard to imagine using the solenoid, but so that would have been nice if someone had said, but, you know, we're not getting this right-hand rule with a perpendicular thing, that'd be good. Yeah.
So why is it, like, worse to use the sphere for the HCAP? Like, I don't know.
For the same reason, for this boosting business.
Yeah.
So
you
what
can't
happens?
split a sphere up sensibly in eta, because the whole point is that when you remember eta, well, you can, but
the fundamental thing. Now think about this, okay? When you let's see, what you need is you need something that is independent of your ignorance. This is absolutely a really not your. I don't mean you. I mean ignorance. You know, there's a reason we make cylindrical detectors, and the reason we make cylindrical detectors is a priori you can't know when you take a parton from a proton and a parton from another proton, or a proton from a gold nucleus or another one, and they collide. You don't know their relative momentum. You know that they're almost certainly not equal. The muon, you know they were equal. But you could have something that's, you know, got 90% of the momentum and 10% of the momentum. And so in the end, because momentum is conserved, the whole thing gets boosted in one direction. And so you need to ask your questions and formulate your problems in such a way that the answer is independent of your ignorance of the motion along the beam direction. And so that means the cylinder is a more natural shape simply by virtue of the fact that if you boost it all in one way, it's still going through the sides. And with a sphere, what's happening is you're getting things all pushed to one side. And it's just, it's not going to be independent of your ignorance. And so that's why we do that. Now with the muon guy, you have knowledge. And so because the momentum is, by God, 0, spherical geometry is the right way to go. But and as you guys know, for the pseudo-rapidity, you get something with a delta pseudo-rapidity of 1, and then it gets smaller and smaller and smaller. And this is absolutely wrong, because, you know, but you know, it gets closer and closer as you go forward. And that means something that is this big, this guy here is smaller, but it's not smaller in the frame where the two partons have exactly balanced momentum. In that frame, they'd be the same size. But this shrinking is because of the relativity that you're learning about. Because it gets boosted forward, the cones get smaller. So it's a relativity thing. And so the whole business with pseudo-rapidity, the point of pseudo-rapidity is it is invariant to boosts along this direction. You know, and that, you know, you don't, when you're first learning relativity, you don't talk about what we call Lorentz invariance all that much.
But you guys did.
Yeah,
right. Well, that's really cool, because Lorentz invariants are key. And it just really boils down to, like, the mass of an object is Lorentz invariant. The mass of an object is the same in all reference frames. And so consequently, we use mass. The delta rapidity is the same in all reference frames. So we use those. And that's why these are chosen. It's because the things we don't know, we don't have to know. Because if we look at it in this frame, or if we boost it in some other frame, you get the same answer.
Okay. All right. Well, thank you very much, Dr. Lincoln.